Hello everyone, video 1 of module 6. In this video we check the internal forces and displacement and generally the result of analysis. So let's start with displacement. So we had a little bit talk about displacement because we need it for troubleshooting. Now we just checking some displacement to see what we have. So if I come here, for example, for earthquake loads, and I want to check, for example, earthquake loading with positive eccentricity, I am in this plan. So whenever I come close to any of the joints and it's been picked, you can see the result. So currently the result is in meter. Because its displacement is better to go for millimeter, so I'm changing this one to Newton and millimeter. So when I'm coming here, I can see the result in millimeter. So U1 is 4 millimeter now because this is X in positive direction. And if I move up, you see that it's increasing and a little bit rotation happening here. The reason is you have few walls here, but you don't have too much stiffness the other side. That's the main result. So if you come here, you can see U1 is 31 millimeter. And in 3D you can do the same. So you can see the top displacement here, how much is it. That doesn't give you any indication because you need to see the story drift. For example, if U1 here is 45 millimeter, U1 here is 31 millimeter. That means you have 14 millimeter displacement here. That means this 14 millimeter is a bit high for 3 meters high, and but depends on the criteria. If it's just a light steel structure with cladding, there is no brittle material, it may be accepted. You guys need to check your local standard and design criteria to make decision about that. So basically this is for displacement. What we have here, we can go for user defined and automatic, as I said. So if you go for user defined, you can scale it up or down, and you can make it a bit more exaggerated to see what you actually want to see more clearly. Then you can go for draw the contours. That contours mainly is useful for shell. So if you come here, for example, UX, and then press apply, you can see the color is based on the amount of displacement. If it's more, you can see different color. If it's less, you can come up to red and purple area. So that's how it shows. And again, you can have this wire shadow. If I apply, you can see this is the original shape of the structure, but this is the deformed shape of the structure. The other thing you have is showing user defined values. You can select maximum and minimum range for displacement or any internal forces, and that shows you what parts are exceeding that displacement or internal force limit. For example, if I put here from 10 millimeter to 30 millimeter and then press apply, whatever is less than 10 millimeters coming with one color, which is purple. Whatever is more than 30 millimeters is coming with that dark blue color. And this is what you can use. Also here you have some other options here. We're not going through them at the moment. We just again, this is for preliminary courses of SAP, so I'm just addressing some basic things that you need for run the model and check the model. So you can do the same for all other load combinations. If I come to envelope, that would be different. That would be the envelope of all displacement for all load combinations. So if I, for example, choose envelope S and apply, you can see the color is very different because the majority of them at some specific load combinations going to the maximum. So generally this color code doesn't give you any information for envelope. Envelope generally showing you the worst case scenario you may have. So you cannot follow any clear pattern by envelope. All you can see here is the worst case scenario. So this is for displacement in general, and we now showing internal forces. So if I come here for internal force, I can choose forces for frames and shells. So let's check frames at first. For example, CombiU G2, I can select here I want to see stress or force, and also what type of force I want to see. I want to see axial force, shear force, moment, or torsion. So for example, I'm selecting axial force and press apply. So you can see here the numbers, all axial forces based on value, because here show values is update. If I put field diagram and just put it here, then you just see the diagram. You cannot see any number, but if you be here, then you can see. Let's change this one to kilonewton and meter. Yeah, so 1334 kilonewton, for example, is the axial force of this pipe. So you can have a look at in more detail. Let's select, for example, top frame. In group we have top steel frame, select, show selection only. Yep. Now you can see the numbers are bigger because these values are comparing to the maximum of the values here. This is how it will be scaled. You had some bigger values below, that's why the number here was not very big. And you can see some things here. For example, in axial force, there is no axial force here, so could be a mistake in the model, or could be because of transferring load to somewhere else. You can see the same here, it's not going to the end, so it's actually coming to the brace. But in the middle ones are different because they are not braced. So when they are braced, the bracings are participating. But you can see here you have, for example, compression, which is red. Here you have tension. So we need to see what's happening in the behavior of a structure and why this is like that. Again, I'm telling you, if SAP doesn't show any error, it doesn't mean that there is no error. So this is not very normal that you have tension or compression like this. There must be an error in the structure. You see some columns don't take too much load. So we need to go through this and see what are the causes and fix them up. Internal forces is the kind of last stage of checking the accuracy of the model, and still we see some discrepancies here, which is normal. You just need to find it and fix it. If you want to see the numbers, you need to come here and again show values and apply, and now you can see the values. So if I rotate it a little bit, and go closer, you can see the numbers here clearly, and also on other elements. So you can do the same, for example, for shear. If you come here, you can see the shear. The other option you have, you can right click on the element, and when you right click, it gives you the diagram of that element with the combination. You can change the combination. You can say I want to see different values. For example, I want to see axial, or I want to go for minor direction, see what's going on here. This is major direction, and you can see the deflection. Then you can come here and scroll value or show the maximum value. If you come here and stay moving, you can see these numbers at the right side. They will change based on where you want to move. So it's not necessarily maximum of all of them for maximum shear, maximum moment, and maximum deflection. But if you put show max, they're showing you the maximum locations. If they are exactly the same like this, they show you the same. They could be in a different location. So for deflection, you can see you have few options. One is relative to the beam ends. That means this deflection is relative to the beam end. So if you have any deflection here because there is another beam here and that beam deflect, it's not showing here. It's from 0 to 0. If you go for absolute, then it would be different. One side could be more, one side could be less, because this is exactly the value you have, including everything. So here, if I change this one to millimeter, you can see here is 65 millimeter, 64 millimeter, and here is 7. If I go to relative to the beam minimum, it's showing 55 millimeter. If I come to the end, you can see it's just 6 millimeter. That means this beam from end to end, we have something maximum about 20 millimeter displacement. But if you add everything to the support, to the base, then the number could be way bigger than that, and even the pattern is different. Depends on the accumulation of the displacement of each joint or each location. Okay, so this is for information of the beam and internal forces. You can try different, and also you can check the stresses. S11 is along the element, so if I press apply, you can see the stresses here. Then S12 and S13 are the stresses in major or minor direction. So S12 is in major direction, S13 is in minor direction, which is horizontal. So the numbers could be very small. And here you can choose, is it a stress max or a stress mean, or which point you want to see. When you go for envelope, then you have maximum and minimum of each envelope. So you can select that stress max and stress mean. Makes more sense, because this is how you use them. Generally it takes time, because when you say envelope, it's checking all combinations together and give you a number. So that was SVM. So if I go to S11, you can see it gives you different values because you have maximum and minimum. So if I change it to megapascal, which is Newton and millimeter, now the numbers makes more sense. So from minus 23 to positive 9. So minus means compression, plus means tension. And likewise for axial load. So minus in compression, plus is tension. Okay, so those are for stresses of element. Let's see why we had irregular compressive loads on the frame. There must be a reason. As I said, we need to review the result of analysis. We need to review internal forces to ensure the analysis is accurate enough to move on for design. Otherwise, many people just see, okay, SAP doesn't have any error, so we can simply go and start our design. But this could be very dangerous. Let's have a look at what we have for frames. So I'm just showing all elements. You can track the logic behind internal forces by checking the displacement. So let's have a look at the displacement. So I'm coming here to one of our grids and just moving to the middle part almost, and now I'm showing, for example, gravity loads. So okay, so let's see what's going on here. Okay, you see a little bit difference in displacement here. The reason is, if you remember, we just for practice added 2 piles for some columns and added 1 pile for some other columns. Actually, the loads are pretty similar, spans are similar. So when you put more stiffness for some of them, you see the displacement is not regular, and you see the difference between these two. Now let's move on to other grids. Okay, you can see here a big change in displacement, which is not normal. Compatibility of deformation is very important, guys. So here you see the displacement between other actually piles and these piles are considerable. So you need to make it logically similar. Otherwise, you have some extra forces. The reason could be the springs are not defined properly. There are many reasons. You need to find the reason and fix it up before moving on for design the elements. So let's have a look at internal forces here and see what does it show. So if I come here and press this, I can see axial forces. I'm going to field diagram. So because of the column loads, it's not very clear, but if I change this one to kilonewton and meter, I can see here 39 kilonewton, 89 kilonewton and 95 kilonewton. So it's changing, and the reason of this change is because of the difference in deformation we have for different parts of the element. So if I move on to other areas, you can see when you're going to the end, these numbers are become more logical. So they are negative under compression, so there is no positive anymore, because positive means this side wants to deflect more, this side doesn't want, so that causes tension here. So that's why the axial force here was positive, not negative. So I'm just showing you the items you need to check. You need to thoroughly check the modal deformation, the deformation due to gravity and lateral loads, and internal forces. You need to see the logic behind transferring load. If you don't have such a step increasing in load and suddenly something miss here, that means there is something wrong. Here is okay because you have a wall, and when the columns reaching here, you have a shell element here and load will be distributed. So it's logical for me. I don't have any issue with that, because actually retaining wall is participating to take load of this column, which is pretty normal. You have a deep beam here between piles, and that deep beam can help you to transfer load. But you need to ensure that what you have is correct before moving on for design.